So let me introduce the speaker a little bit before he starts his talk. So today we have Dr. Franco, who's from the University of North Florida, and he's my very good friend, and we work a lot with him during past 3 years. So I think today he present some results together with me and Dr. Dumitru from the University of North Florida. Please, your time, Jose.
Thank you all for organizing the seminar. Thank you for inviting me to give a talk. This is fun group, fun time to share some of our work for everyone, and thank you for the opportunity. So I'm going to talk about the means of K matrices. So I'm going to start with a little bit of an introduction with means of scalars. Then we're going to move on to a little bit of the history, well, the generalization to means of matrices, and that also works for operators. So talk a little bit of the work of Professors Kubo and Ando. Then I'm going to, and I'm just basically going to touch on the most basic concepts that we need to move on into our topic. So then I'm going to talk a little bit on the history of how these means get generalized to more than two matrices. So how we do means of several matrices. Then I'm going to tell you about the construction of the Renyi power means. This is recent work with Dr. Dumitru. We introduced these means that are related to a function that is used in the definition of the Renyi divergence or quantum information theory. But so we denoted them Renyi power means because of that connection there. And then we're going to look at inequalities related, norm inequalities related to this means and the power means. And this is where I have some of the work that I did with Hoa. This was 2018, I want to say. So around that time, we proved that conjecture from Bhatia, Lim, and Yamasaki. So there, I have a little bit of that there. So we start with the means, and most of you are probably familiar with means of numbers. So we start with just positive scalars, and we have the arithmetic mean, which we denote by A nabla B, which is just going to be the mean that we know. We can also do a weighted version where we could do, for example, TA plus 1 minus TB, would be the weighted arithmetic mean. We also know the harmonic mean that we denote as with the exclamation mark. And we would get A inverse plus, or the arithmetic mean of the inverses, and then we take the inverse of it, and then we have geometric mean, which is well-known geometric mean that we denote by A sharp B. So all these are very, very standard. The quasi-arithmetic mean or power means, also known also as binomial means, would be weighted by a parameter T and a weight P. In that case, then we have, or a power P. In that case, we have the definition of the P powers, or the weighted arithmetic mean of the P powers of A and B, and then raised to the 1 over P. P in this case for scalars would be okay to be all real numbers. Any real number is good. Of course, when we consider P, we would consider it in the limit sense. So those are some means that will be connected to what we're going to be working on, or we're going to be looking at today. So the first thing is, how do we generalize these concepts to matrices? So to do that, we can, of course, just grab the formula and put in matrices in place and see what we get. But that theory becomes a little bit not very satisfying, because right away you have issues with some things. For example, if you have powers that are not integer powers, then you are going to have some sort of issues there. So the right setting for them are going to be the Hermitian matrices, because they behave more or less like numbers. So I do mention some differences, that we have the non-commutativity of the product of matrices. We know that, so that can get in the way. But other than that, you kind of want to think about matrices as complex numbers, generalizations of them in any case. And in that case, the Hermitian matrix will play the role of real numbers in that sense, because the conjugate with the transpose, which is the adjoint, will be the same as the matrix itself, which is something that real numbers do satisfy. If you do complex conjugate of a purely real number, then you would get the same thing back. So that's a way to do things, and turns out that, as naive as that sounds, it actually has we profit quite a bit of that of setting ourselves in that setup. So again, the definition, sorry, I didn't read it. The definition of a Hermitian matrix, where the adjoint, which is the conjugate transpose of the conjugate of the transpose of the matrix, is going to be equal to the matrix. So the matrix is invariant under that operation. All right. We do need a little bit of order here, because we need to talk about, for example, we talk about means, with the exception perhaps of the arithmetic mean, we're going to mostly restrict ourselves to positive numbers. So we need a concept of positivity as well for our Hermitian matrices now. So the positivity we're going to have is that concept of positive semi-definite, and that's going to allow us to have a partial order relation on the set of, or on the space of Hermitian matrices, by basically redoing whatever we did at the level of scalars. So you say that for the relation of A being greater than B at the level of scalars is true if and only if A minus B is positive. So we're going to do the same thing. So we're going to say that A in terms of matrix is going to be greater than B if and only if A minus B is greater than 0. But what do we mean by A minus B greater or equal to 0? Well, this is what we mean. We mean that the matrix is positive semi-definite. So what does that mean? It means that when you do the inner product of AX with X, you always get a non-negative number. And if you always get a strictly positive number whenever you put a non-zero vector, then you say that it is not only positive semi-definite, but you say that it is positive definite. So if you have a strict positivity condition here. And in that sense, then we can have a partial order, A greater or equal than B, if and only if A minus B is greater than 0. So what have we done so far? So we have means of numbers, positive numbers. We now are trying to set ourselves up to define means of positive definite and positive semi-definite matrices. So to do that, we introduce the concept. We introduce the concept of having the inequality A greater or equal than B. So now we need what is the key step to define all these things. And that's going to be the concept of functional calculus and monotone functions. And to do that, I forgot I have to talk about the spectral theorem before that. So to do that, we're going to rely on the spectral theorem. So if we have a Hermitian matrix, an n by n Hermitian matrix, then the spectral theorem tells us that we can write A as a linear combination of its eigenvalues and spectral projections Pi. So this decomposition will allow us to define a function in the sense of functional calculus. So f of A will basically just evaluate when f is a function from an interval that contains the spectrum of A. We're going to define f as the sum from I equals 1 to n in this case of f lambda I, and then multiply times the eigen projections, the Pi. So we do have that way of defining functions on matrices now, because if you think about it, we want to define functions, but in general, the functions we can define on just regular matrices is somewhat limited. I mean, we do have a little bit of a limited scope of things we can do. We can do powers, we can do additions, we can do products, but after that, once we're done with the integral powers, we're kind of restricted at that point. So that's why the setup of the Hermitian matrix happens to be so useful, because now we can define a lot more functions by using this definition right here. The other way you could think about it is if you think about it in terms of diagonalization. If you don't like thinking it in terms of a sum or a series, then you think about it in terms of a diagonalization. And of course, the advantage of looking at it in the way or in the form of a series is that you can generalize this to operators. So you can just talk about operators, not necessarily just matrices. But for the purposes of our talk, we're going to restrict ourselves to positive semi-definite matrices. So in this case, then it is reasonable to consider then unitary matrix U that diagonalizes A, and we have the expression for A as U. Then the diagonal matrix with the diagonal entries being the eigenvalues of the matrix, and then the conjugate transpose or the adjoint of U. And then when we define f of that, we just define f of the eigenvalues, and we keep our matrices U the same. Okay, these two are equivalent ways of seeing it. So there's no, I'm not giving you two different ways of doing it. They're equivalent. All right. So now that we have functions to play with, and we're going to restrict ourselves to, technically I could relax this, but I'm going to restrict myself to positive reals to positive reals. And I'm going to assume in this case that A and B are positive semi-definite, actually positive definite if I define my function to be only defined on the positive numbers. I have to put the restriction that A be strictly greater than B. I didn't notice that I had my restriction here. Could be relaxed. Nonetheless, let's assume they're positive because most of the functions we're going to be working with are positive. So the monotonicity, we define it the same way, the operator monotonicity, the same way you would define increasing monotone functions in the case of real value functions. So in that case, then f of A is greater than f of B. If and only if A greater than B, if that is satisfied, then you say that the function is operator monotone in that case. All right. So with this, there's going to be a connection, or there's going to be, well, the wrong word to use connection right now that I'm going to actually introduce what a connection is. There is a link, let's say, between operator monotone functions and matrix means. And that is due to the work of Professors Kubo and Ando that actually made this connection. There's an affine isomorphism between the space of operator monotone functions and the set of all means, operator means. And there's going to be more detail about this here in a second. But let's look at their definition of what a mean of matrices would be. And they require some conditions that a priori seem like they are rather necessary and obvious, but then turns out that a lot of the extensions of means that we do don't satisfy all these properties. So they seem to be so basic, but at the same time, they actually turn out not to be as easy to achieve. So the first one is monotonicity. So if you have that A is less or equal than C and B less or equal than D, then this binary operation sigma, which is going to be right now called a connection, will satisfy that the connection of A and B is going to be dominated by the connection of C and D. So that monotonicity condition is actually rather strong. This one, we don't get this in some of our, the means I'm going to talk about later in the talk. Then we have this transformer inequality that basically says that if you operate first, if you first take the mean of two matrices and then you conjugate it by X with its conjugate transpose here, then you get something dominated by what you would obtain if you first conjugate and then take the operation, the binary operation. The last thing that we require for a connection is that it is upper continuous. Yes, and that is that if you have a sequence of positive A's that converge to a positive, possibly semi-definite A, and similarly for BNs that converge to possibly semi-definite B, then the means of them converge to the mean of A and B. And if in addition you have the normalization property that if you take your positive matrix to be the identity and you operate it with itself, then you get the identity back, then that happens to be a mean. Moreover, if you have now a mean, it is said to be symmetric if and only if you have that the symmetry condition A sigma B equals B sigma A is satisfied for all positive definite or semi-definite, if you want to extend it, matrices. All right, so now we have means. And so what do they look like? Because at the moment, this seems rather abstract. I mean, okay, so great. So can I just define one and see if it works? Sure, you can define a few, but even when you move on to, for example, the arithmetic and the harmonic that we mentioned, they happen to be extended just by replacing the scalars by the matrices. Fantastic. But when you move on to the case of the geometric mean, for example, then the extension is not absolutely obvious. So what happens then is that there is an operator monotone function, and this is the, to me, one of the most important and most remarkable parts of the theory of Kubo-Ando, the theory of Kubo-Ando on means of operators, that tell you that exactly how you can construct. Basically, if you have an operator monotone function that satisfies the condition that f of 1 equals 1, then you can actually define a mean. And you define it by this formula that, confession time, when I started working in this field, and this was when right about the time, like a year before I met Hoa, and when I looked at this formula, and in particular the one for the geometric mean, I would hate it. I don't want to work with that. That's so ugly. It's so horrible. You know, like, why would anyone do that? And as you start working on this, you just get this huge appreciation for that formula. You end up loving it. You're like, this is great. How else would you define it? But when you see it at first, it's like, this is just so messed up. Like, who would ever think about defining things this way? But it's not. It really is. It's really, really important, and it works really well. And it is actually a very elegant formula that we get to enjoy working with, right, Hoa? All right. So here the function f sigma is called the representing function of sigma. And it's satisfied that f sigma of x is basically 1 sigma x. So if you plug 1 and x into the definition of your sigma, then you recover your function, and vice versa. All right, so in that sense, then, as I had advertised, the arithmetic mean happens to be the exact same thing as we know. Skip this one for the moment. The harmonic mean is the same thing we advertised earlier. But the geometric mean, then you realize that it's a little bit different. And if you were just to plug in A and B as matrices into just the definition of the geometric mean that we normally would have, you'd get the square root of A times B. Just from that outset, you have the problem that A times B is not necessarily a positive semi-definite matrix, even if A and B are. And then taking a square root, it becomes a challenge. Of course, you can still do it, but the problem is you end up with something that is not necessarily positive semi-definite, so not great. And then you can start like adding things that you would like to have, and eventually you realize that it is not very obvious to define this mean. In any event, their theory allows you to explicitly write it out, and turns out to be rather useful. All right. So then we're gonna jump onto a little bit of a brief history as where the means of several matrices, where are we at, and where did we start? Because the first thing you would think, well, not the first thing, definitely not the first thing, but one thing you would think once you have a good solid theory of means of two matrices, you think, what if I want a third one? You know, we always want more. And that's very typical of mathematicians. I can prove it for this. What about this much more? You know, like we always think in that sense. So it's like, so what about three matrices? Can you do it? And of course, there's some that you could extend rather easily. For example, the arithmetic mean, we know how to do it. We just say, well, if you just have A, B, and C, you just say A plus B plus C divided by 3. Fantastic. We're done. We're in business. But then you think about the the power means, well, you would probably think about the geometric mean and you try to see, so how can I do it with a cubic root? How do I go about that? And then you realize, oh, this is a lot more difficult than I thought, and you put the book down and go to something else. Or you insist, and then you end up proving it at some point. Not me, other people. All right, in any case, for the power mean, you could substitute in the AIs strictly automatically into the formula, and you do get something. And depending on the parameters T, you may get things that are more, that are a bit nicer than others. You can get some inequalities to come out. And by the way, this definition, to my knowledge, the first time it appeared was in the word of Bawat and Subramanian. I hope I'm saying the names correctly. But this was, if I am correct, was in the early 90s. No, it was before that. Anyways, I don't have the reference, but this happened rather early in the theory, and I should have had that date. I don't remember exactly. And we can look it up if need be, but this happened rather early. But then you get to the means, the geometric mean, for example. How do you do that? And the geometric mean then already poses a bit of a problem. So the first approach, there were some approaches, but the first somewhat successful, or actually rather successful approach, was by Professors Ando, Chico Lee, and Matias, that they sought out to extend the geometric mean to first just to 3 matrices, right? Then they did it for K. But they start by telling us what conditions would you need. And for example, you would need monotonicity consistent with scalars, the invariance with respect to unitary transformations, and as a sort of 10 different properties that they think a geometric mean would need to satisfy. And then they seek out to construct something like that. And they do a rather elegant approach by iterations. And I don't see where I can annotate. Anyways, but the idea is the following. So if you have 3 matrices, think about, you have your, I wish I could draw it. I thought I had. Do you know if there's a way I can draw on the screen?
I don't know, Jose.
well, okay, it's okay. I should have thought about that earlier.
You can share the other screen if like one mode or something. You can draw there. I'm not sure you can draw this.
Let's see. Maybe there's I guess I could share. Okay, yeah, let me do that. Let me open another screen then, and go to. Let me try to do that. I failed there. Let me open a notebook here so we can work on it. Wasting time here. You see, I didn't have a lot to say, so
That's fine, man.
I'm strategic here. No, I'm kidding. All right, so let me share this other screen. That's a good approach. So let me stop sharing. I want to share something else. I'm going to share my notebook here so we can talk about it here. So let's say you have 3 matrices, A1, A2, and A3. Let's put A3 a little bit out here. And you wanted to compute the geometric mean of the 3. Then what they do is they basically, you know how to do it for 2. So you would just do the geometric of these 2 guys. Let's say it lands here. Then you do the geometric mean. And Hoa drew this picture on my board several times because he had some ideas for other research projects that I'm not going to disclose unless he wants me to. But he he drew this picture several times. And so then that would be your first iteration. So he calls this T of this matrix, this vector A, which would be just the vector. And here you just do A2, A3, then you go to A1, A3, and then you do 3. You see my handwriting. You now get to see what my students suffer through. Oh, well. So you get that. That's your first iteration. Then you go ahead and do the geometric mean of this guy with this guy, and that's going to land somewhere here. and then continue with the edges. And eventually they construct a sequence of vectors that eventually will converge into a geometric mean. Now, if you want to do 4, well, now now that you did it inductively, you do it inductively, you know how to do the geometric mean for 3. So now you would grab your square, or not square, but your polytope with 4 matrices. And I probably drawing it is not going to be great, but I'm going to give you the idea. At least you would construct your first. Now A is gonna excuse my abuse of notation. Here would be A1 through A1, A2, A3. This one will be A1, A2, A3, A4. So in this case, then you're gonna have the geometric mean that you would just define as the limit of this sequence of t to the k's, and you would get the geometric mean of A2, A3, A4, and geometric mean, and you can see what we're going to be doing. Geometric mean of A1, ignore A2, A3, A4, and you define, continue like that. I skip 1 until you get A1, A2, A3. But now you know how to see how, if you want 50 matrices, how this will become really, really, really difficult to compute by hand, because you're each time have to compute the n-1. So this is rather expensive, and so we need other ways to do it. However, that was a good approach that gave us, I think I moved, trying to write stuff, I moved around a bit, but that was a right approach. That was a good approach that gave us a generalization of the geometric mean in that fashion. So here is the abstract construction, where this right here, I'm gonna steal the colloquialism from my professor in grad school. He called this the Harry Potter invisibility cloak. So when you had the hat, means that is excluded from the list, because he put on the invisibility cloak. I thought that was rather cute, so I'll steal it for a second. All right, so basically this is the construction of Ando, Lee, and Matthias, or is Matthias. The name, the pronunciation, I will assume I'm saying it right. So then Bini, Maini, and Polini just modify their argument by weighing things. When you do the construct this vector, you assume your triangle again, then you weigh things around a little bit, and that gave a little faster convergence. And so they have a similar construction, and it satisfies the 10 properties that we needed. But unfortunately, this is still computationally rather expensive. So there is a better approach. That is the way that we can actually compute this, and it is by due to the work of Moacker, Bhatia, and Holbrook. Well, Moacker first, and then Bhatia and Holbrook independently define a geometric mean by way of minimizing the sum of the squares of the distance. And here the distance is going to be defined by the 2 norm, the 2-Schatten norm, which will be the square root of the sum of the squares of the singular values of the matrix. And then they evaluate that at the logarithm of this term that we should start becoming familiar with. I don't think we have a good name for this. We should have a name for this. Would be this expression. Maybe Juan knows a name.
No, that is Riemann and distance.
No, I'm saying just the a to negative a half, b a negative a half. Is there a good name for that term? Because we use it so much that we should have a name for that, you know?
Seems like you can name that at Jose, for example.
Oh, that would be fantastic. No, I don't think it will fly, though. I'm sorry. People will not go with Jose's term. So sad. Anyway, so continuing, sorry for the I am, you can see I'm not a very formal person, and I joke a lot, so, and I have Hoa right here to bounce jokes off of, so it makes it worse. So anyways, I'm blaming you a little bit for my breaks. All right, in any case, so we have then the minimizing of the sum of the squares, the unique positive definite, or semi-definite rather, matrix that minimizes distance is going to be the geometric mean. Now, computationally, me personally, I don't know what to do with this form. When I try to compute this on, say, if I program it in Mathematica or Python or whatever, I don't know how to compute that. However, this right here gives me a much better way to do it, because you're looking for an equation. You're trying to solve an equation. So what you end up doing, then you can program it easier in this sense by trying to find iterative approximations to the solution. So that is a lot better computational. So it turns out that these two geometric means, the unique positive definite or semi-definite solution to this not algebraic, but this matrix equation, it corresponds to the minimizer of the sum of the squares of the distance. So along those lines, Lim and Palfia went ahead and tried to approximate the Karcher mean by using the fact that, and this, by the way, due to the constructions, was known now as either the Riemannian mean or the Karcher mean, and then there are different names for it, but it's just a generalization of the geometric mean. So depending on the author, of course. So what happens is that if you take the limit as p goes to 0, this right here, and if you choose, I guess, omega to be 1/2, this will recover the geometric mean. So using that idea from scalars, they sought out to approximate the Karcher mean by way of the power mean, and they defined this power mean as follows. So they looked at the geometric mean. So they did a convex linear combination of geometric mean of x with all the AIs provided, and they set it equal to x. And then they proved that there exists a unique positive definite solution or semi-definite solution to this algebraic equation. Now it is algebraic. So and they did this by using basically they proved that the function that defines the right-hand side is a strict contraction with respect to the Thomson metric. And then using a fixed point theorem, then they tell you that by iterating the function that defines this right-hand side, you iterate it, and that converges down to a solution. So when you're trying to program something to find this right here, it is really, really easy to program it, because what do? Well, you just create yourself a loop where you apply the function over and over and over. You start with the identity, for example. You start with any matrix, and you just create a loop, say whatever you feel like. Computers nowadays, you can do 1,000 if you want, 1,000,000 if you want, but this converges super fast. The convergence of this equation, whenever I'm looking for numerical examples, I do probably 10 or 20. I mean, it converges so fast. By the 20th iteration, the computer doesn't have enough decimal expansions to actually detect a difference. So it's really, really fast convergence. So this is a huge improvement, because then what you need to do, and they prove, is to compute the geometric mean here. All you have to do is create a sequence that goes down to 0. So as t goes to 0, they prove this goes down to the Karcher mean. So you start taking small and smaller t's, give yourself a sequence, and eventually you find your convergence down. So you do kind of a convergence in a diagonal fashion, and you can compute in that way, or get a good approximation rather, to the Karcher mean. So this is this was a very good approach and a great progress. But what caught our eyes, so what I started thinking about was, and this happened, if I must be honest, happened this last summer. We were locked down due to COVID, and I was going to bed, and I just had this idea. Juan and I had worked on a paper just recently where we changed a geometric mean by a Renyi, this matrix related to the Renyi divergence. So this term that is essentially kind of like a not optimal, but almost like a geometric mean, if you think about it. If this would commute, then it goes back to the weighted geometric mean. So it kind of looked to me, and by the way, I didn't introduce the weighted geometric mean. I'm going to write it here in 1 second. but it looked to me like it was very similar to what we had done. And I was just going to bed and I said, what if I could change this geometric mean right here for that one of those Renyi divergence like terms? Can we get something? Can we actually get something interesting? And that kind of started this project. So let me tell you what this is, because I did not give the definition. I just realized. So the weighted geometric mean is going to be the same thing that we did for the geometric mean. So that term that looks ugly, but it's not. It's good in the inside. And then instead of raising it to the 1/2, you raise it to t and then 1/2. That's what I mean by the weighted geometric mean. So if this would commute, this would actually correspond to b to the t, a to the 1 minus t. So that would be the weighted geometric mean. Okay, so I did not include that there. So let me continue, because I realize the time is kind of going fast. So we need the Thompson metric, which is just going to be the infinity, the infinite norm, which is the maximum of the eigenvalues if it's positive definite, or singular values if it's just any regular matrix. And then we're going to take this this function that is central to the definition of the Renyi and kind of encompasses all the sandwich Renyi entropy, the regular Renyi entropy, and the alpha Z Renyi entropy. All of them are encompassed here. So what we seek out to do, let me jump to the definition so you see what I'm trying to do. I'm trying to define the Renyi power means in the exact same way that we defined that Lima and Palfia defined the power means in their paper. But now instead of having the geometric mean here, instead of Q, I have this Q that corresponds to the Renyi. The idea is kind of the same. Is I have to prove now that that the function that defines this right-hand side is going to be a strict contraction with respect to the Thompson metric. Because if I get that, then I get that the fixed point theorem actually guarantees that this converges. If you iterate, it converges down to just one unique positive definite or semi-definite solution, and then you define that as your Renyi power mean. So that's what we're going to do. Let me show you kind of a little bit of the idea of the proofs. Unfortunately, I talked more than I realized. But the lemmas that we need, this was proved by Lima and Palfia, turns out to be rather necessary. And this is the one that made things stick. This is the lemma that I was afraid was not going to work whenever I started trying to work to do this. So that in fact, if you do the distance between the Q x of a, q being just the Renyi term, and then the q of y and a, that this would be bound. I didn't even need the alpha. I needed something less than 1, but I needed just strictly less than the distance from x and y. I didn't know that was going to happen, and it took a little bit of finagling around to get it, but turns out that it is true. And basically, you require this inequality is due to Bhatia, that you can drop the z out, and then you basically have to go back and forth between the infinity norm of the vector eigenvalues to the infinity norm of the matrices, and then using the fact that the argument of the logarithm is positive, the logarithm of the eigenvalue or the eigenvalue of the logarithm. So you play with those things, because not everything works in general. So you have to be flipping from one setup to the other. But a little bit of notational calisthenics actually get you through to what you actually need. And it works out that it is, in fact, that this is satisfied. So using the last two lemmas, these two lemmas, and I'm not going to go into the details because I don't think I have time, but it is, I'm halfway through the talk and I have 20 minutes, but 20, if that. 15. I actually went too long. But basically what we have is that this has a unique positive definite solution. And to prove it, you define this function f here as the right-hand side of the equation. And then you prove that it is a strict contraction, meaning that the distance from f of tzx, which t is a plane that role of alpha, and then tzy, that is going to be less than actually the distance from x and y, strictly less. So we proved that by using the previous two lemmas. For example, when you do the convex linear combination, then that the lemma from Lyman-Palfia gives you that is going to be less than the distance between the maximum of the distance between q of x and y for ai. So the maximum of taking the maximum over the i's, that's what I want to say, of this distance. And then by the lemma, we proved this is less than the maximum of the ti's times the distance of xy. So it is a strict contraction. And then the fixed point theorem gives us in fact has a unique positive definite solution. So we do have what we need to define this as the Renyi power mean. We called it Renyi because it sounds like, no, because it's related to the Renyi entropy divergence. So it makes sense that it would be called that. You see, I didn't call it the Franco Dumitru mean because nobody would call it that anyways. So anyway, so we proved a lot of properties that they're satisfied. Unfortunately, this wouldn't be called a mean in the Kubo-Ando sense because it's not monotone. So we don't get monotonicity, unfortunately. And but we do have like a lot of things. We do have a lot of things like consistency with scalars. We do have, for example, that this kind of invariance condition that if you do the mean of A1 through AM and you throw in X, if you get X back, that happens that X was originally the mean of those A1 through AM. So that's a very nice condition. You get permutation invariance, of course, because the equation that you started with is permutationally invariant. And then you have unitary invariance as well, which is nice to have. Then your scalar homogeneity. You see whenever the AIs commute, you get a power mean. That's what we call it, the power mean. I forgot to mention that. And unfortunately, we chose the alpha in a way that then turned out to be 1 minus alpha in the power. So a little bit of a thing but at the time that we started proving this, we realized, oh, we have to change the whole paper. So now we leave it. So that's kind of that. So, but you see that if you multiply each matrix times a scalar, then what you get coming out of that is going to be that power mean of the scalars. And then you just have to modify your weights so that they actually still add up to 1. So that's all you really do. Anyway, these are interesting, but not the most important part of what I want to talk about. What I want to talk about is the relation in norm with other power means. So at the moment we have 3 different power means: the one of Bauwat and Subramanian, the one of Lyman-Palfia, and then the Renyi power means. So so we're going to look at a class of inequalities that they were started, I think, correct me if I'm wrong, Hua, but I think is the first one to prove any of this was Yamasaki, and then in a paper prior to Bhatia, Lim, and Yamasaki. So then they started working on that idea of Yamasaki, where he looked at a Kubo-Ando means of 2 matrices. In fact, he also looked for Kubo-Ando means of K matrices, and then compared them in unitary invariant norm to a non-Kubo-Ando extension of the exact same mean. And they came up with a rule, or like a rule of thumb, let's call it, that the Kubo-Ando means are usually bound above by the non-Kubo-Ando extensions in norm. And that, for the most common norms, actually holds true, but then Hoa, Dr. Dumitru and I constructed a Kubo-Ando mean and an extension that do not satisfy this norm minimality. So we came up with a counterexample to that rule of thumb, but seems to hold a lot, but is not true in general. In any case, you can extend that to K matrices, and what would qualify as a Kubo-Ando mean for K greater or equal than 2 is that they satisfy monotonicity, transformer inequality, and upper continuity. So you would have those conditions. Now, we do not have the beautiful theory where you can relate them to an operator monotone function, except Palfia is actually working on a generalization of the concept of monotone functions. He published that actually recently to K matrices, but I don't know if there's still a connection, or if this matrix, if there will be a connection between these means and operator monotone functions in several variables. So at the moment, I don't know if there's anything in that way. But the theorem that we, the first one is joint work with Hoa and Dr. Dumitru. And we proved the case for p greater or equal than 2 and less than infinity for this mean, where the Lyman-Palfia means of a power means of several matrices. Actually, we proved it for operators, is bound above by the we proved it for matrix. Take it back. It's bound above by what Subramanian, and then we tried once we introduced the Renyi matrices. We said, what if we have the power mean bound above by the Renyi, because that would be actually the Kubo versus non-Kubo-Ando. This could be an issue with the numerical approximations, because remember, both means are approximated numerically, but we found, I called them in the paper pseudo counterexamples, because yeah, there are matrices for which we had counterexamples, but they're so close that it could just be an point errors in the computer. So I'm not ready to just say this is categorically not true. It may be, there may be a proof out there where PT and R1 minus T are comparable, at least for some special cases, perhaps. But I couldn't find a proof, and I found some pseudo counterexamples. So how am I doing with time, Hoa? Do I have time to just talk briefly about the proof, or you cut me off now?
I don't. You still have time, but I think we can omit the proof. How about that?
We can, yeah, I can just talk about the key lemmas, and then I move on to questions. Yep.
But by the way,
sounds...
I think I see a typo on your theorem. It should be T, not alpha, I guess.
T.
The condition P greater.
Yes. T over Z and then 1 minus T. You see, copy paste will do us all in. Thank you, Hoa. Yes, definitely, yes. Good point there. Because I changed here the mu alpha, or 1 minus alpha to T, and then I forgot to change it here. Perfect. Thank you so much. This alpha happens to be 1 minus T. In fact, so this would be 1 minus T, and this would be T. Yeah. Thank you. Yeah, so that, where alpha equals 1 minus T. All right, so here's the lemma. This is the lemma that makes this last proof stick. And it should remind you of like Furuta inequality, but it takes a lot more work than just that. So basically, it is a log majorization, or if you want to think about in terms of, we needed just the trace inequality. So think about trace of this less or equal than a trace of this, and it compares R, which is going to be taken place by the Renyi power mean, and then Q of the Renyi with any A, which is going to be the expression we're going to have when we expand out the right-hand side of the definition of the Renyi power means. So this one actually took a little bit of work, and it was nice that it did work, because it was, let me put it this way, the reference I put for this lemma in the LaTeX file is called, in Spanish, sufrido, which means suffered. So if you would look at my text file, this is the suffered lemma. So it took quite a bit of work to make it work, and that's why we ended up with this types of conditions on P that is not, it seems weird, but it is just as tight as it could get to for this to actually work. Anyways, here was the proof, and then with that, the proof of the theorem follows, but I will take a time now for questions.
Thank you very much, Jose, for interesting talk. Do you have any comments or questions to our speaker? Do you have any?
I have one for myself. How can I talk so much with just 32 slides?
you know, you explain very detailed picture of geometry. That's very interesting.
Yeah, yeah.
And okay, so I don't hear any question. I have question for you.
Tell me.
So you said about the Renyi mean does not satisfy the monotonicity, right?
Right, right, right.
That happens for every alpha and z, or just we cannot prove that because like he I have a lot of he has some papers, and even all people when they study Renyi alpha z Renyi entropy, they study the domain of alpha and z where they have where Renyi
Convexity.
entropy satisfy the data processing inequality. So I would guess maybe you might have monotonicity somewhere, not for every
True, true.
advice.
Even if we don't get monotonicity, well, I did look into convexity. I will talk about that. But remember that when Hiai and Data and Odener and all of them look at this, they look at it at this Renyi, but inside the trace. So they look at when it's jointly convex inside the trace. So I couldn't find at least any good results. Here I have some with the log majorization as well, but I couldn't find a good result like just for the matrices, But now that you mentioned z equals to 1 would be the good place to start, That would be interesting to see because z equals 1, then you don't have a big power outside. So yeah,
Yeah,
that's a very good question. We should definitely look into that. Yeah. Z equals to 1 would be my guess that one may be monotone, which is not bad because z equals to 1 relates to the original Renyi divergence, right?
yeah,
Because when you have the alpha equals to z, that it would be the sandwich Renyi. But when z is equal to 1, that would be the regular Renyi. And then you have alpha z. So that would still be worthwhile looking into it. That's actually a very good question. Yeah. Yeah.
yeah.
Yeah.
And Dima, do you have questions?
Yeah, I have a quick technical question. I'm not familiar with all the tools that you're using, but I saw that you're using the logarithm of a matrix. So of course I'm familiar with matrix exponentials, but so is it the same idea? You just expand, and so that's why you need the positive definite for the matrix in order for you to be able to take the logarithm.
Correct. Can be done both ways. So with the series and also with the just functional calculus approach that we had back here, just by using the spectral theorem, right?
So you just take the logarithm of the eigenvalues and then times the projection eigenprojections.
Exactly.
Oh, interesting. Okay, thank you.
Yep.
Can I have a question, Franco?
Mm-hmm.
Okay, so can I take a look at your slide about when you define the Renyi power mean?
Oh, okay. Yes.
Yeah. Okay.
No power. So
You
right
define
here.
it like the minimizer of this, right? So
Right.
the idea is you try to give a definition of power mean for many matrices, right?
Correct.
So for example, in this case, suppose ME2, do you have the explicit formula for your R alpha Z?
You see, you hit me in the feelings right now. That's one thing we tried a lot, and we were not able to find a closed form because Lima and Palfia do have a very nice closed form when when k is equal to 2 in this case, or m in this case is equal to 2. We were unable to find a good closed form. I wish I had one. Definitely does. The one thing I can tell you is it definitely does not agree with the Lehman Palfia, of course, because they're monotone. But they are actually very close, not only in the sense of not only in norm, they're very close even entry-wise. When you compare the matrices that you get from the Lehman Palfia and this, they are very close. So but we don't have a good closed form. I wish we had, and that would be very interesting to actually work on. So I would hope that more people get interested in this topic, because we can actually look for the things that I haven't proved that we can prove. Is a closed form could be the monotonicity that Hoa was mentioning. That was a really good idea. Then there were all the inequalities between the PT and the Rs. We don't know how they behave. I do have, as I said, pseudo counterexamples, but I don't have them. Like, I cannot tell you exactly for which alphas and z. So it's another worthwhile object or things to play with. And then anything else that has been done for the Riemann-Palkia power means would be worthwhile looking if anything would be satisfied here at this level. But yeah, closed form would definitely be that. Yeah, it's right up there, but don't have one.
Okay, thank you, Joseph.
All right. Do you have something else? We still have time for questions. So actually, you know, from your talk, I have some ideas for next, you know, project.
Well, you know, every time you have ideas, I am glad with that.
yeah. So, like, you know, the first idea I want to mention, even on this slide. So here you use Renyi function, right? Renyi matrix function. But if you switch that a little bit, you change, for example, AIX. So you will go from Renyi entropy to fidelity, to quantum fidelity.
Right.
Yeah. So given that, you know, they are related, but the equation should be different.
Yes.
So when you just interchange X and AI, yeah, you get quantum fidelity. But I think they define like
you know the one. You know the one lemma that I couldn't make work with that, because I did look into that. It was this one. This is the one that if you exchange them, I couldn't make it work, because then now your X goes outside, and then it didn't work for me. That doesn't mean it's not true. I just probably need another approach. But this is the lemma that we would need to make work.
Yeah. You know, we still have second direction. We still have second direction. So because, you know, you have different ways to prove that the inequality one has a unique solution. So like you may use strictly convexity or something like that. Yeah, this is one approach, you know, posted by Riemann-Palkia. But another approach, yeah,
you know what you do gain when you exchange them, though? You are able to then multiply, because you would get some like x to negative a half AI x negative a half, then or to 1/2, then you would get x to negative a half x to negative a half. So you would get a kind of like a geometric mean of the inverse of x. Yeah. Right. Well, in some cases, right, but sort of like a geometric mean equaling, in this case, the identity, which is kind of like what Riemann-Palkia used to prove their closed form of the power means for 2. So yeah, that may be a better approach, because and then you should have some sort of, but wouldn't you have concavity instead of
strictly convexity, strict convexity? So yeah, you can use strict convexity to prove that, you know, the and yeah, like.
But I'm afraid we'd get concavity rather than convexity. Anyways, we can look at it. Yeah, we can look at it.
Theorem to prove the existence, and then use a strict convexity to show that. Yeah, actually, you know, the critical point is the unique. So, you know.
Right.
Yeah, that is the main idea of this. And we have another direction is we can get the inequality one using quantum divergence. So you use Frechet differentiation, and then, you know, you arrive at formula 1. But that is about least square problems. So you skip the first step. Like you skip the first step, right? You have least square problem, and then you need to differentiate that by critical point, and you skip that step. So I think it's good. It's still good.
That is one thing that I was considering as well. Now that you mentioned it, the least square problem, what kind of divergence would be needed for this Renyi matrix to actually, so going backwards, you know, like, so basically what you said, instead of going to the least square problem first, then go from this algebraic expression, the equation solution to equation, now to the least square. And I wonder if there's some quantum divergence or any kind of, like, let's just say any divergence that would give us the Renyi as the solution to the least square problem.
Mm-hmm. All right. Yeah, we'll talk with you more about that. Yeah.
I'll look forward to it.
Yeah. Do you have anything else for our speaker? Okay, so so thank you again, Jose, for interesting talk and
Thank
for
you.
joining us. Yeah. I would say, yeah. And next week we have a talk delivered by Dr. Dmitry Glotov from Auburn University. So I will send out an announcement later, so you can see him there, right? All right. Thank you very much for joining us, and see you next week.
Thank you.
Okay.
You wanted me to stay here, Hua, or do you want to make another Teams meeting?
Please stay here, Jose.
Okay.